All right, here we are. Wow, this has been a strange week. We had Tuesday off, and then we have this today. So I don't know what's going on down there. The weather up here isn't really that bad, but who knew? You never know when they tell you snow is coming. You do what you have to do. But anyway, I think there's nothing. Once in a while, it's nice to do this online, and it's very convenient. I don't know if your other classes are online or not, but I live very far away, so I wanted to make sure that I didn't have any problems getting down there. So here we are again. All right, anyway, so what we're going to do today is two things. We have to go over the chapter 11 problem set number 2, and we're going to at least start the sample midterms. So this way, we can wrap up everything next Tuesday. And as we discussed, we can have the actual test on Friday the 4th, which is a week from today. And then we'll be all set with that. And then the week after that, we'll have our normal classes. And then after that, you have spring break. Woohoo. All right. So let me get these open. Hopefully your calculators are out. And because we're going to need them. And we're going to go through these and look at the different ways we can solve these problems with our calculators. And as always, you can choose the one that you want to use. If you notice, it never actually says you must do it this way or you must do it that way. Well, it just says test the hypothesis, and it's up to you to decide which approach to use. But no matter which approach you use, ideally on the test, you should write out the steps that you're following. The advantage of doing that is that, first of all, it helps you avoid making mistakes. But secondly, it means that if you make a mistake, I can give you partial credits if I can see what happened. All right, so think of it as an insurance policy. All right, anyway, so why don't we go back to this one? Now, we start out with, this is the second problem set. Notice here, we've got this table. Now, already you should probably see that what we're doing here is testing two samples that are not independent of each other. They're somehow related to each other. So this is that last case that we saw in the chapter for testing hypotheses about two means. The first three, remember, all assumed independence. Case 1, case 2A, case 2B, which we took care of with the first problem set. Now we're going to focus our attention on the cases where the populations are not independent. And then at the end, we'll have a problem which has us test hypotheses about the proportions. Okay, so let's begin with this one. Now, we see here that a new drug is being tested to see if it lowers cholesterol. We choose a sample of 8 volunteers and we take their readings before and after the medication. And the readings are listed here. Now, this time, if you notice, I've already included the differences in the last column of this table. So when you put this information into your calculator, you don't really have to enter either of these because you already have the differences. Okay, so in other words, as far as we're concerned, these numbers are almost irrelevant. What really matters to us is the differences. So we can think of these differences as a single population or sample. And so when it comes time to entering data into your calculator, although it's true that it can figure these out, it can figure out the differences for you. If it's already here, you might as well take advantage of that and simply type in the differences into your lists. Okay, you don't really need to type these because the differences are already here. And that should speed things up a bit. So anyway, here's what we're going to do. We're going to test the hypothesis that the mean readings are equal before and after. Now, here's the question. What are we hoping to find? We're hoping to see that the readings are going down. Now, remember, the way we define differences is the mean of the first sample minus the mean of the second sample. So although it sounds backwards, if the readings are going down, that means that the differences should be positive. All right, so in other words, you notice here, for example, with this volunteer, the reading went down by 5 points, and therefore the difference is positive. So the company that's producing this drug is hoping to find positive differences. So that being the case, this is a right tail test. Right tail because we're hoping to find evidence that the mean difference is positive, which implies that the drugs are working. So we're going to set this up as a right tail
Oh, Professor, sorry,
Yes.
but can you just go over again, like what wording told you is a right tail and left tail? Like that's the only thing I'm
Okay,
like, having
yes.
trouble with.
Okay, good. First of all, remember mu D, as we're using in this section of the chapter, the mean difference is defined as the mean of the first group minus the second group. So what that means then is that here, we're hoping to find that the readings are getting smaller, because remember, we're trying to lower people's cholesterol. And so if they are smaller, then the differences will be positive. All right, so in other words, you see that like here we've got this person's readings went down by 5 points, so the difference is positive because we're calculating the difference as the mean of the first one minus the mean of the second one. Now, this person also had a drop in score, and so their reading is +5. This person, unfortunately, their reading went up by 1, so they have a negative difference. Okay, now this person, their score went down by 7, so therefore it's a positive difference. So if that's the case, the drug company has an interest in finding positive differences because positive differences are an indication that the drug is working. But they don't want to go out and market this drug unless they have strong evidence that it's actually working. So to be conservative, we're going to set up the null to be the mean difference is 0, but the alternative, which is in this case what we're hoping to find, is that the mean difference is positive, because positive difference in this case means the drug is working. Does that make sense?
Yeah, it does. So
Okay.
what would like the numbers look like if it was a two-tail test?
Well, if it was a detailed test, that would be a little different because we're just trying to find out if there's a difference at all. In other words, it's either the difference is 0 or it is not, where we don't actually care if it's positive or negative. We just want to know if it's different.
Okay.
All right, that's a very different scenario than what we're seeing here. Here it matters a great deal if the difference is positive. So that's what we're testing for. Now, by the way, in the second question, I've done it in reverse to make sure we have practice with both types of cases. Let's just look at this one for a second to see the important difference. This one, in this case, what's happening is that a marketing company has spent a bunch of money advertising a product on TV, and they're hoping to find that household spending on this product has gone up. All right, so here's the spending that these people did before on this product, and here's how much they spend on it afterwards. In this case, we want the numbers to go up. And that being the case, if they do go up, the differences will actually be negative. So since
if the numbers go up, it's a left-tailed. If the numbers are going down afterwards, it's a right-tailed.
That's right. Now, I know it sounds strange, but that's how it's because of the way we define the differences as the original values minus the new values.
Okay, that makes sense.
I know it sounds strange, but so you have to get used to it. Okay. All right, good. So anyway, so we'll see that one in a few minutes. We'll do this one first. And so anyway, so there's the data. So we'll set it up as a right-tailed test. And you're right to be so concerned about this because if you get that backwards, you almost certainly will not get the right answer. So anyway, we'll assume that alpha is 0.05, as is so often the case. Now, the test statistic is this thing, which you might remember from the slides. And by the way, this is why we save this for last, because it is different than what we're used to seeing. And so remember, D bar is the average difference, and SD is the sample standard deviation of those differences. And of course, is the sample size. That hasn't changed. So now the big question becomes, how do we calculate these numbers? Now in the slides, you see there are formulas for calculating D bar and SD, but we don't really need to use those formulas because we have access to these amazing TI-84s, which enable us to type in data into lists. So before we go any further, what I'd like you to do is go to your calculator and type the differences into list 1. Okay, so if you forgot how that works, what you're going to do is stat, edit, go into list 1 with your arrow key. First though, if there's old data there, go to the top with the arrow key and hit the clear button, and that'll erase everything. Once that's done, type in these numbers, and in order to get out of this mode, you have to hit second mode. okay, to get out of the list mode. All right, so I'm going to give you a minute to go ahead and type these. And since they're integers, you should be done pretty quickly. So you'll type them in, and then we'll carry on from there.
We're typing in volunteer, reading before, after.
No, you don't need those. No, absolutely not. And see, here's the nice thing about this. All we need is the differences. So just type differences in one.
All right.
Now, when we did this the first time in class, we did actually enter these two just to get some practice. But because the differences are already here, I very kindly put them in there. You don't need to bother typing in reading before or after. All we need is the differences. Now, the volunteer part, you never need anyway. It's just 1 through 80. So you don't even have to bother with that. But if you don't have the differences, you will need to either calculate them yourself, or else you can type these into the lists 1 and 2, and then you can ask the calculator to calculate the differences for L3. But here it's already there, so you might as well put it to good use by typing these into L1. Okay, so why don't you take a minute and do that? I know you're fast. Your texting thumbs are really fast. So you can go ahead and type those in. And when you're done, we'll do the actual calculations. All right, let me know when you're done. Oh, also, I'm going to post this on Blackboard, all these solutions. Plus, also, don't forget, this is being recorded. So there'll be a recording available. I'll see. I think there might be enough room on Blackboard for this. But I'll let you know. Sometimes I put it in my own YouTube account if there's if I'm worried about the space considerations. But I think there is room in Blackboard for this. All right, so what we're going to do now is we're going to see that there's multiple ways of getting at these solutions. So it's up to you to decide which one you like the best, but just make sure that when you're doing this on a test, that you write down the steps so that I can give you partial credits if something goes wrong. Okay. And plus, this helps you avoid making mistakes too. Now, if you do once you've entered the numbers into L1, we're going to ask the calculator to do D bar and SD for us. It can do that, although the labels are slightly different. But we'll see as we go along how to find out which is which. So here's what you're going to do. Now go back to Stat, and this time hit Calc. That's the middle menu, and choose the first option, which is 1var stats. And it's going to ask you for the list. Which list do you mean? And if it already says L1, you're good. But if not, in order to tell it list 1, you're going to type the second button followed by a 1. That it interprets as L1. Okay. You can tell by looking at the 1 button directly above it in the tiniest imaginable print, it does actually say L1. That is there because that's one of the second functions. So once you've done that, it comes back with all the information you need. It's got a huge string of numbers, but the ones we need are what it's calling X bar, okay, which we're calling D bar, which is 3.375. And then SX is what it's calling, what we're calling SD, and that is 3.6228. And finally, at the bottom, it's reminding you that the sample size N is 8. Now, all you have to do is plug those in to the test statistic and, the normal way, and you should end up with approximately 2.635. And by the way, we can go over this again on Tuesday when we meet again. If any of this is unclear, we have time to go over it one more time. All right, so if you've got that, then the next challenge, of course, is to look up the critical value, which you can get out of a table. Now, here you have to remember that with this type of test, the degrees of freedom is n-1, because we're thinking of the differences as being a single population. So surprisingly enough, the degrees of freedom is n-1. And of course, this is a right tail test, so we'll have alpha or 5% in the right tail. And you can either look it up in a table, or we can use, yes, INVT. So if you go to second vars, number 4 is INVT. And it's going to ask you for 2 pieces of information. It's going to ask you for an area, and it's going to ask you for the degrees of freedom. Now, if you're using the original TI-84 like I have, it's going to assume you mean the area below the point you're looking for. So instead of giving it an area 0.05, you'll give it an area 0.95. And of course, 7 degrees of freedom, as you can see over here, and it's going to come back with a number of approximately 1.895. If you put in an area 0.05, it'll come back with negative 1.89457, which means you just got it backwards. The number you actually want is positive 1.895. Anything above that would be considered to be a rejection of the null hypothesis. All right, so is everyone getting that? Okay, it's very bizarre being online after having been back in the classroom for a while, because I can't see you. You know what I mean? I can't tell if everything's going well or not. So I'm going to rely on you to tell me if something's wrong.
Where did you get this 7?
Oh, because the sample size is 8.
Oh, n-1, right?
Yes, exactly.
Okay.
All right, there you go. Perfect. You see, that's exactly what I mean. You got to tell me if you're not getting something, because I can't see you. Okay, and even if I could, well, it's not the same, is it? No, I've got these little tiny maybe pictures. That doesn't tell me anything about whether you're following or not. So, all right, anyway. Now, the test statistic, as we just saw, is about 2.635. So it's pretty clear that we're going to reject the null hypothesis. Okay, it's too large to be consistent with the null hypothesis. It's way out in the right tail. So therefore, we reject the null that the means are equal. Now, this is good news for the drug company, isn't it? Because remember, we're looking for evidence. You got 3.204, really. Why don't you go back and look at your list again and see if you've got the exact same numbers. Yeah, see, I can't come over there and look at it. This is so annoying. Go back and double check your list. That would be my first thought, that you maybe made a typo in your list. Okay, and then go back and run that same calc function. And see what happens. One more thing too, I just want to remind you that the number, it gives out a lot of numbers. Make sure that you're looking at SX, okay? Because it's possible that you're looking at the wrong value. On this calculator, the one we need is labeled just plain SX. All right, let me know what happened. Oh, okay, yeah, and if you're still having issues, you can show it to me on Tuesday and we'll figure it out. But I suspect that there's a typo involved, or else, like I said, that function gives a lot of numbers. And so you want to make sure that it's the one that says SX. You may have been reading the wrong one too. Those are the 2 things that might have gone wrong. All right, anyway, so we're actually done with this part. The test statistic is in the rejection region. We can reject the null that the mean difference is 0 and accept the alternative that the mean difference is positive. And that's exactly what they were hoping to find. that tells us that we have evidence that the drug is effective and they can go out and market it now. Now, what if you wanted to use the p-value approach? Okay, no problem. First of all, I just want to remind you what you're actually looking for when you do the p-value test. You're looking for the areas that are more extreme than your test statistic. So this orange shaded region is going to be your p-value. And you can see it's going to be a very, very small number. The question is, how do you find it? All right, so what you're going to do, and by the way, here it turns out that there's two equivalent ways of calculating the p-value. Interestingly enough, because we already did all these calculations, we can actually take advantage of that. I'll show you how. If you go to stat test t-test, and remember, even though you've got two populations here, we're using t-test because we're only thinking of the differences as a single population. If you choose the stats button, it's going to ask you for these numbers, but you already have them because we did those up here with the 1var stats function. Not only that, but if you haven't messed around with the calculator and changed something, they're still in those cells. If you notice, it filled them in for you. Okay, so as long as you haven't done something else in the meantime, the numbers you got from the 1var test, 1var stats rather, these numbers should still be visible and they should be in your calculator.
So it's possible, I'm sorry.
Yeah, go ahead.
So it's possible just to do this entire problem by calculating the differences in L1 and then doing the p-value approach.
Yes.
And then that's all you would have to do?
Yep, that's right. Yes. Now here, if you notice, because we did calculate these statistics, 1var stats, it actually went ahead and plugged them in for us. All you have to do is make sure it knows that it's right tail test, and guess what? It's going to come back and show you the same values we just calculated, including the test statistic of 2.635. The key detail here, though, is that the p-value is only 0.0168. And that is well below alpha, which we know means that we should reject the null and accept the alternative that the mean difference is positive, which implies that the drug is working. Okay. Now, if you did not calculate these statistics, no problem, because when you come down here, when you go into this mode, instead of choosing stats, you could have chosen list or data, sorry, data. And then it's going to ask you for the list. So this is probably the quickest way of going about this. And we've done this before in the class. Just make sure, because when you say data, you're telling it, I want to give you the actual data rather than these summary statistics. So that means all you have to do is, after you've entered list, your data into list, you need stat test, to test data, tell it where your list is, and make sure it knows you're doing a right tail test. And you get the right answer. Look at that.
So you would accept the new value, the 0.16, and not the original given value we found, right? Because if this falls within the region.
Well, if you're using the p-value, all that matters is how p compares with alpha.
Yeah. So since alpha was what,
0.05.
Yeah, 0.05. This
Right.
is less than 0.05. So therefore you accept it.
Therefore, you reject it.
Reject it.
Right. In other words, low p-value means you reject the null.
Oh, okay.
I'll tell you why. If you forget about this, here's the way to think about it. The p-value could be thought of more or less as the probability that the null is true. That being the case, a low p-value indicates that it's not true.
Okay.
So if you forget, but I was hoping that this little graph, now you see here, that p-value is very tiny. This whole shaded region is 5%. So if the p-value is less than 5, we must reject the null.
What if it was over 5, you would accept it?
That's correct. Or you fail to reject is the way you technically should say it. You're saying that we don't have enough evidence to reject the null. So a large p-value means we can't reject the null. A
Okay.
small p-value means we do.
Oh, okay. I thought it was the opposite. Okay. Thank you.
Oh yeah, you better get that straight before the test rolls around.
Yeah. Right.
But does this diagram help at all? Like the p-value was what was it, 0.0168?
Yes.
So but the shaded black region is 5.
Mhm.
So in other words, you see two things are going on here at once. The test statistic is greater than the critical value. And as a result, the p-value is below alpha. So this diagram, I'm hoping, will show you why these two approaches are really the same thing. The only way that this can happen is if the p-value is less than alpha. Either way, you reject the null, because it just means that the data are not consistent with the null hypothesis. It's like, imagine if I told you that, the government thinks that the average age of all Americans is 29, and then they grab a sample and the average age in the sample is 54. Well, that means something's wrong. So that's kind of what's happening here. Okay, so either one of these, they mean the same thing. Test statistic being greater than the critical value or p-value being below alpha. They represent the same information. Now, in this day and age, the p-value thing has gained in popularity in recent years as calculators and statistical software have become available. In fact, some books, I should go so far as to call the p-value approach the modern approach, because if you look at any software, including Excel, it will always give you a p-value. It almost never gives you the test statistic. The critical value. That's your problem. For whatever reason, this is what you're more likely to see with a calculator or a software product. But they're just essentially the opposite sides of the same coin. So either way, you've got the right result. Okay. All right. Anyway, with all that being said, let's go on to number 2. Now, this one is different because here we're hoping to find evidence. The spending, we want it to go up, but that implies a negative difference. Okay. Because remember, we're defining the difference. If this is population 1 or sample 1, sample 2, and remember we define mu d as mu1 minus mu2. This number will be negative if mu2 is greater than mu1. And that's what we're trying to find out. That's what we're hoping for. We want to see evidence that our advertising increase people's spending on this product. Okay, so guess what? Your challenge now is to go to your list and enter these numbers. These are prices. So there's dollars and cents, and some of them are negative. You can either put these into L2 if you want to save L1, or you can just erase L1, either way. But if you put it in L2, make sure that you tell the calculator that when we do these techniques, okay? In my solutions, I'm assuming that you're using L1, but if you're not, you obviously have to change that. All right, so this is a left-tail test. We're trying to find out if the spending has gone up as a result of this advertising campaign. Yes or no? Is it less than or is it not? If so, that means we'll carry on and run these ads some more. If not, we'll try something different. So it's a left-tail test. Also, I just wanted to point out here that they really need hard evidence of this. So they're going to choose a very low alpha, 0.01 this time. So what I want you to do is type these into one of your lists, and then we can carry on. But basically, the rest of it is exactly the same. It's the same test statistic, the same everything. All right. So let me know when you're ready. Yeah, I know they're not integers. That's going to make it a little trickier.
after you type the values in L1, where do you go from there?
Okay, hit second mode.
Okay,
Yeah, that'll get you out of there. Yeah, that's an important detail because otherwise you're going to be stuck in there forever. Hit second mode.
and then how do I see the values like we did before?
Oh, did you type it in L2 or L1?
L1.
Okay, so if you save the L1s and you want to look at them again, you have to go back into the lists and they'll just still be sitting there.
Okay,
So yeah, you can always go back and forth into the lists, but
gotcha.
to get out, you have to hit that second mode. Otherwise, like I said, now, by the way, on the test, it's not a calculator test. If you're stuck with something on your calculator, you can ask about that on the test, okay? There's no problem with that.
Okay, perfect.
So, like I said, it's not a calculator test. So if you can't figure out how to get out of your list mode, I can show you that during the test.
Okay.
I can't tell you the answer to the question, of course, but I can tell you how to get out of the list mode. All right, good. So, by the way, we're going to do a bunch of new ones. When we get to the sample midterm, we'll have an opportunity to do more of these same exact problems. And if you still don't get it, then we can do office hours. All right. But I think once you've done these and then done them again on the sample midterm, you should be fine. Especially the calculator. Once you get it, the thing is, often there's this one little thing that trips you up. Once you understand what that is, then there's never any reason to ever make mistakes again. Okay, it's like that one little thing you didn't know, like second quid or second mode actually. Once you know that, that's it. You can do it forever. All right, so here's the test statistic. Now it's the same one that we had before. So we're going to do this in two ways, and you can decide which one you like the best. You can do stat calc. Number one is one var stats, as long as it knows what list you've used. And if you didn't use L1, make sure you change that. And these are the ones that we actually care about. Now in the calculator, again, it's labeled X bar and SX, but in our formula, we're calling them D bar and SD. And then you plug them in. Now this time we got a really small test statistic. The differences aren't very great. And if anything, they're in the wrong sign too, because if you notice, most of them are positive, and we were hoping to find them to be negative. So it doesn't look like this advertising did a whole lot of good, but we have to prove it. All right, so the critical value, now this is a left-tailed test. The entire area of alpha goes in the left tail. It's 1%, remember. From here, yes, I circled it. And the degrees of freedom is n-1. This time we only have 6 in our sample. So it's n-1 is 5. And what you might want to do, you can go to the table, or you can go to your calculator, and remember here under the vars menu, second vars menu, you've got number 4 is INVT, which stands for inverse of the t distribution. The area you're looking for is 0.01. And the degrees of freedom is 5. And that should bring you back to negative 3.365. Now, if you've got one of the other calculators like the 84 CE, when you get to this point, it can let you choose between left, right, and center. The calculator I have always goes to left. So you just have to be a little careful. But if you choose the wrong one, you'll probably get the wrong sign anyway. So if you're not sure how it works, you might want to leave it on left by default, just so that it lines up with what the TI-84 original version is doing. Now here, if you called this right, you just would have gotten the positive value, 3.365. It's the center one you have to watch out for. That's only meant for two-tailed tests. But anyway, you look at it, our test statistic is 1.1516, but our critical value is negative 3.365. We're not even close to the rejection region. And so therefore our conclusion is that we do not reject the null, that the mean difference is 0. So therefore, there's not enough evidence to show that the advertising campaign actually led to higher sales. Now you notice we word it very carefully. We don't say that the advertising campaign was a flop. No. That's a different thing altogether. That's a matter of opinion. Formally, what we're saying is that we don't have enough evidence to show that the ads produced higher sales. Okay. That's the end of the story. That's what we were trying to find out. Now, the p-value approach, just like before, we can do this in two different ways. If you go to stat tests, t-test, if you ask for the stats menu, it will ask you for these numbers, which you just got through calculating with one var stats, or at least you did today. On the actual test, you could skip this altogether and go directly to this approach. Okay, that's up to you. So if you do this approach, you're going to get the mean. And remember, this one is what we mean by D bar. And this is what we mean by SD. And it's going to ask you, you're going to remind it that it's a left-tailed test. You go ahead and do the calculations. And guess what? It's going to come back with a whole string of numbers, but first you'll notice that it confirms that we correctly calculated the test statistic. Look at that p-value. Oh my God. It's enormous. And this is why. Look at that. Wow. It's almost the entire distribution. That's why it's so massive. And remember, the p-value can only go up to 1. So again, our decision is that since the p-value is above alpha, we do not reject the null. And that tells us that we don't have enough evidence to suggest that the advertising is working. Finally, the last one, the quickest one, in my opinion, if you go to stat test to test, instead of picking data, instead of picking stats, you can pick data. When you type in data, you're telling the calculator that you know all the original information, not just the summary statistics, not just the mean, not just the standard deviation. You have access to all the data. And you're telling it that it's stored in a certain list. So if you used L1, you have to tell it that, or whatever list you chose to use. It does need to know that this is 0. Remember, this is the same thing as saying. Okay. And remember, make sure it knows that you're doing a left-tailed test. And there it is. It comes back with your p-value. And since it's so high, that tells me that P above alpha, we do not reject the null, that the mean difference is 0. All right, so you got so many choices. Well, I suspect I know which one you're going to use. The quickest one, well, that's okay. That's fine, as long as you understand what you've done. They all lead to the same point. It's like there's so many roads that lead to the same point. There's not just one way to get to our classroom, and you follow the path that's probably the quickest. So that's what we might do here, but it's good to know that these other options are here. All right. Who knows? Maybe there's some reason why you do need to know these numbers. Maybe the company will turn around and say, well, what was the sample mean? Or something like that. But to just test the hypothesis, all you really need is the p-value and the alpha. All right, now those are done. Now we're going to do a test about the population proportions of 2 different populations. So here we go. And this is the last thing we did in the chapter, by the way, if you want to go back and reread the slides. A researcher wants to know if the proportion of retirees is the same among men and women. So you can see there the sample number, the sample size for men is 80. We choose 90 women. Among the men, we find that 5 are retired, so X1 is 5. For the women, 8 are retired, so we call that X2. And the sample proportions we calculate ourselves, and they're defined as X over N. So among the men in the sample, 6.25% are retired. Among the women, it's 8.89%. So the question is that enough of a difference to conclude that the difference, that the retirement percentage is different? If you notice, they're just asking if the proportion is the same. And you know what that means? Two-tailed test. Because we're not looking for evidence that one is greater than the other. We're just trying to find out if they're equal or not. And that's when we have a two-tailed test. You might remember that we use the letter pi in this book for population proportions. So the null is that pi1 equals pi2. And the alternative is that they're different. Two-tailed test. Level of significance is 5%. And here's the challenging part, the test statistic. Oh my God, look at that thing. All right. So let's see, I'm going to split the screen so you can see both of them at once. There you go. So if you plug in the numbers, you'll see that the p-bar is the average proportion between the two population, or two samples rather. And that turned out to be 0.0765. Okay, so we average them out. This is actually a weighted average because the number of men and women is different. So it's about 7.65% average for everybody. We plug that back here into the test statistic. And let's see, oh boy. I guess we don't need that up there anymore. Let's do this. All right, I think you can see everything now. So you plug them in, and it's a bit of a headache, but when you're done, you should get your test statistic equal to negative 0.646. Now, we know from experience that that's a very small test statistic. Usually in order to reject the null, we need to be at least, let's say 1.6, 1.7, maybe even higher than that. This probably is not going to be rejected, but we still have to go through the formality of proving it. So we start by looking for the critical values. We know there will be two of them because it's a two-tailed test. Plus or minus z alpha over 2, which implies that 2.5% of the area is in either tail. And for this one, you can go to the normal table, or you can go to our old friend INV norm. Okay, so with second vars, go to INV norm number 3. The area is, I'm listing here as 0.975 because I'm looking for everything below z 0.0025. The right tail, as you know, is 0.025.
Oh, Professor, what was the given alpha?
Oh, alpha in this case was 5%. It's right here.
All right, perfect. Yeah. Thank you.
Okay. Yes, so 2.5% is split up into either tail. And now, by the way, always make sure that with this INV norm, you're going to be using mu 0 and sigma is 1 because this is the standard normal distribution. And it should already be there, but if it got changed for some reason, you can make sure it's 0 and 1. Otherwise, you're going to get the wrong numbers and you'll never know why. So it comes out with 1.96. So of course, that means the right one, the one in the right tail is 1.96 and the other one is negative 1.96. But of course, the test statistic is not even close to either one of those. So we're not going to be able to reject the null. So I've drawn that separately down here. Give me a minute to catch up and I'll show it to you. All right. So yeah, it's in there. It's not in the rejection region. Therefore, we do not reject the null that the proportion of retirees is equal among the men and women. So in other words, basically the way this can be interpreted is that there's insufficient evidence to show that the proportions are different. Whoops. Now, you're probably wondering, what about the whole p-value approach? Of course. So this time it's a little more straightforward because there's really only one way of doing it. So go to the stat test and look for 2-prop z test. There's not going to be a t-test for the proportions. The only thing you have to decide is whether we've got one proportion or two. Here it's two, of course. So choose number 6, and it will ask you for the following details. You need the X's and the N's. And of course, at some point, you have to tell it that this is a two-tailed test. And boy, that's a big p-value. And so because it's so big, we do not reject the null. And that's it. So we're done. Well, now, how was that? Was that hard? No, not really. But, there might be some little details that you're still not sure about. What I recommend you do is go through this again. Maybe try it one more time without looking at the answers. It depends on the individual. Oh, yes, I'll do that right now. Okay, so you can go over to the second vars function. You get it wrong. Okay. I wonder what's going on with that.
Where did the 0.975 come for the second bars for the
Oh,
area?
okay, here we go. Because what I'm trying to find here is this critical value. There's two of them. I'm looking,
Okay.
and so if the area in the right tail is 0.025,
Mhm.
everything below that must have a total area of 0.975 because they have to add up to 1.
Yeah, no, I understand that part. My question was the critical value. How'd you know 0.25? Is that was that just a given?
Oh, because that's half of alpha.
Half alpha, that was, okay.
Yeah,
All right, thank you.
yes, alpha was right here, 5%.
Yeah.
That's a good question. Yes, 5%. That's our alpha. And so that means half of that is 0.025.
Okay.
By the way,
If
if you're having an issue with your calculator, when it comes to a two-tailed test, you might want to do this instead. You can look up the lower of the two, the negative critical value by doing this. Because the left tail is 0.025. If you type this, it's just going to come back negative 1.96.
Okay. So worst case scenario, just I could leave it like that, but either way, you have to put it on the two sides. So then,
Yes, that's right. Don't forget, then that means there's a positive 196 as well.
yeah, I just forgot to divide the alpha by 2. I just
Oh,
that was because I forgot it's a two-tailed.
That's right. It's two-tailed. Exactly. When it's two-tailed, you must divide alpha in half.
Yeah.
Because the total isn't changing. It's just where is it located?
All right, perfect.
Okay. All right, then. So, all right. I hope everyone's all caught up with that. Oh, well, even better because we're done. So I'll post this document on Blackboard, of course. Actually, I just remembered the video will fit on Blackboard, but it's going to fit under a different category. It's called Panopto or something like that, because let me show it to you. Because we hardly ever do this. See where it says right there, Panopto video? Oh, all right. Well, maybe I shouldn't have done that. Oh, here it is. We did have it. I think once before we had a day where the weather was really lousy. And this should be the video. What day is this? It doesn't even say. But this is where the video will appear. I can put it on my YouTube account if you want, but this is where they want us to put it. Panopto is the name of the software that they use. I think the reason why they use it is because it can provide closed captioning. So if necessary. So I believe that's what the purpose of this is. I don't think you're going to get that if you put it on YouTube. But on the other hand, it's easy to find it, right? So, and in the past couple of years when we're doing all, online because of the COVID, I had quite a few videos in there that they're still there if you want to look at them for some reason. In fact, why don't I show it to you? Just in case. Notice I've got, what do I have here? Mostly music, baseball, and cooking. Okay. I don't know if you can see my videos or not, but you can see, here they are. So if you look under playlists, you'll see there's a whole slew of these courses that I've taught, and they're all listed as being public. So that means you can actually go in here and say, hey, I want to learn more about derivatives. And you can literally watch these videos if you have nothing better to do one night. Um, and then these are a bunch of videos that I saved because I like them. Did you know, I discovered this purely by accident. If you watch a video and there's like this little thumb icon, if you click the thumb icon, it'll actually save it in a list of liked videos so you don't lose it. I don't know. Am I the only one who didn't know that? Probably. But once I figured that out, now I always give all my favorite videos a big thumbs up. And that way I can go find them whenever I want them. But anyway, enough of that fun stuff. Let's get back. Now, here's what I'd like to do. And this is what I did with my other class. For the sample midterm, we obviously don't have time to do it all right now, but I would like to at least look at the fill-ins. And because, you know, we only have one more class before the test, and I don't want to run out of time. So let's take a quick look at this. There are some fill-ins, and these are short answer questions. Now, when I was going over this with the other class, I noticed some of these were not worded as well as they should have been. And so I'll try very hard to make sure that doesn't happen on the test. I want it to be crystal clear, and I mean crystal clear what I'm asking. So like, for example, here, what is a type 1 error? That occurs when you reject the null when it is actually true. Okay, no problems there. And since these are English statements, you know, obviously there's going to be a lot of leeway here. In other words, I'm not going to take points off because you spelled a word wrong or some nonsense like that. As long as I see that you understand the concept, that's fine. What is a null hypothesis? A statement that is assumed to be true unless there is strong contradictory evidence. Okay. So we did that on day one. Now, here's one where I thought afterwards that maybe the meaning of this question wasn't as clear as it might have been. Also, I should have specified, and I'll make sure that I change this for the test, about a single population mean. The whole idea here was just to have you write out the alternative hypothesis. What does it look like when I'm testing a right tail test? That's all. It wasn't written as clearly as it could have been, but this was the intentional answer. Now, on the test, if I find that some of the questions weren't written very clearly, you know, I can just give you the credits anyway. I hope it doesn't happen, but if it does, I'll take care of it. All right, so you don't have to worry about that. Now, by the way, I just also want to mention, this is something, I think we mentioned this once. In principle, you're supposed to use the t-distribution anytime you don't know this population standard deviation, but usually it's more important when we have small samples, because if we have large samples, the results will be almost the same, whether we use the standard normal or the t. So the focus is really on the small samples, but technically, what I should have done is said, the population standard deviation is unknown. Because that's how we basically explained it in the beginning. So I'll make sure that the test is written as clearly as humanly possible. The whole point of the question is just to have you write down the test statistic when we're using the t-distribution. Okay. All right, 5. What size is considered to be large when testing a hypothesis? You might remember from the central limit theorem in stats 1 that the cutoff point between large and small is 30. All right, so a sample of 30 or more is defined as large. 6, same thing. For a two-tailed test of a single population mean, let's change that. small sample or the population standard deviation is unknown. In other words, it's the t distribution, but it's a two-tailed test. That's what I wanted. Oh God, what a mess. That I probably should never do fill-ins anymore. Problems are so straightforward. If the p-value is less than the level of significance, and remember, level of significance is alpha. They mean the same thing. Is the null rejected? Yes, it's just that simple.
So one word answers for the fill-ins are okay?
Yes, if it's warranted, like here, the answer is yes. If just the word
Okay.
yes is all you would have needed, and that's fine.
So you're not gonna require like explanations?
No, not unless it specifically says to explain it.
Gotcha.
Whatever the minimum amount you can get away with and still correctly answer it is fine. Okay, it's supposed to be quick and easy.
Gotcha.
They're not essays. Oh, as far as the samples go, as soon as we're done, I'll be, well, as far as today goes, we're not going to be completely done. I will post what we have so far. Okay. And then on Tuesday, when we completely finish it, I will post the rest of them, because I find that if I put the solutions up in advance, well, it's easy for people to get complacent and say, oh, I get it, don't worry about it. It's this way, you have to work on it without knowing the answers. And I just think that's better. So as soon as we're done on Tuesday, you'll have the rest. Okay. Anyway, now this one is a little tricky. This is nothing to do with the writing. I just want to go through a couple of things here. And you're not required to go through all this explanation. If the level of significance is increased from 0.01 to 0.05, what happens to the probability of a type 2 error? Okay, so the level of significance, as you recall, is the probability of a type 1 error. Just remember that. Now, remember, we also at some point used the letter beta to represent the probability of a type 2 error. The way it works is that if I increase the probability of a type 1 error, that means I'm simultaneously decreasing the probability of a type 2 error. If one goes up, the other has to go down, and vice versa. That's what the premise of this question is. If alpha goes up, that means the probability of the type 1 error is going up, which means that at the same time, the probability of a type 2 error must be going down. Okay, so the correct answer is decreases. You can literally write decreases, and that's all that you need. But I put all this in here to remind you what this question is really asking about. Okay, just in case you started to forget. Okay, yeah, because we haven't discussed this since really day one in the class, or whatever day it was. It was way, way back. Oh, it was a long time ago. Okay, let's put it that way. It's in the slides, but I mean, it was a long time ago. Now 9, when testing a hypothesis about two population means, see, this time I actually specifically said what it was. When is the test statistic based on the standard normal distribution? All right, now you might remember that we broke up all these cases. This is chapter 11, by the way. Remember we had case 1, 2A, and 2B. 2B for independent samples. And then we went ahead and looked at the paired samples. This is the case where we use the standard normal, 2B. So 3 things were true in case 2B. The populations are independent. The variances are not equal to each other. That was case 1, by the way. And the sample sizes are both large, meaning they're both at least 30. So this is what we were looking for. 2B, independent populations, not equal population variances, both sample sizes are large. So these last two are kind of a pain, aren't they? Wow, look at these. I'll try to keep those down to a minimum. How about that? But I mean, it's important to know this, of course. All right, so you see what I did? Basically, it's just asking you which case are we talking about here. And that is the case 2B, where we have independent populations. Variances are different from each other, and sample sizes have to both be large. Now, this one, when testing a hypothesis about two population means when the populations are not independent. This is the case where we had what are called paired samples. This is the one we saved for last. The ones with the tables, basically. If you recall the test, in fact, we can just go back up here and confirm that. What test statistic? Oh, not here, sorry, the other one. The test statistic that we used, let's go back to the very beginning. That would be this case. These are the so-called paired samples. The test statistic is always based on the t distribution here. Okay, so that's what this question is really asking. Okay, all right. Now, since we have a few minutes, I'd like to at least start the first problem here, because again, I don't want to run out of time on Tuesday. I don't think I will, but let's just look at this. These are a mixture of everything we did. So here we have a juice manufacturer that wants to ensure that its orange juice cartons contain at least 50 milligrams of vitamin C per 32-ounce carton. If not, they will have to use a more expensive type of orange in the production process. So they're hoping that this isn't true, but we're not going to do anything unless we have hard evidence that the mean is less than 50. So this actually becomes a left-hand test, because we're looking for evidence that the mean vitamin C content is less than 50. Not that we want to make this change, but we better, otherwise we're going to run into trouble, maybe with the FDA. So at the same time, though, we don't want to take any action unless we have hard proof that there's a problem. So it's a left-hand test, and because we want to be super confident that if we do reject the null, that it's really false, we're going to choose a very low alpha of 0.01. And then we gather up some data. We take 20 cartons, and it's 20. The sample mean is 48, and the sample standard deviation is 2.4. All right, so this is chapter 10. So we know that sigma is unknown, so we're going to use the t distribution. And if you plug in the numbers, you'll see that the test statistic is negative 3.73, which means it looks like we're going to have to reject the null. But why don't we prove it? Let's go find the critical value. Now, there's only one because it's a left-hand test. And in this type of test, the degrees of freedom is n-1. And in fact, any time you use the t distribution in chapter 10, the degrees of freedom is n-1. It's only chapter 11 where we get those crazy formulas. So here the sample size is 20, so therefore we must have 19 degrees of freedom with a tail area of 0.01. So let's find this in our calculators. Use second var's INVT. So the area you can use now is 0.01. And 19 degrees of freedom, and you should get approximately negative 2.539. And you can see, oh, look what happened. That means that the test statistic did in fact land in the rejection region. Therefore, of course, we reject the null. It's that simple. Okay, so you've got the picture right there. And so we conclude, actually, let me split the screen a little bit here. All right, the test statistic is in the rejection region. We reject the null. And unfortunately, we have to accept the alternative that the mean is below 50, which means that the company will have to use the more expensive oranges now. Oh, well. And then as far as the p-value goes, now, once again, the p-value, just remind you, the p-value would be anything that's more extreme than this test statistic. Right here, you can see it's going to be really, really tiny.
You said we're rejecting the null, right? Oh, yeah.
Yes,
Okay.
yes, we reject the null because the test statistic is in the rejection region. Okay, so we reject the null that the mean is 50. Okay, and accept the alternative that it is below 50. Oh, bummers. It's a bad result for the company, but this is the correct result. For the p-value, you just go ahead and say, all right, stat tests, t-tests. This is a single sample that we're looking at. And so go to the stats mode and give it all the numbers that we had. The hypothesized value is 50. The X bar is 48 rather, SX is 2.4. Sample size is 20. Make sure it knows that this is a left tail test. And now, just as I said, look at that p-value. It's tiny. It's so tiny, 0.007149. And so because it's so far below alpha, we reject the null that the mean is 50 and accept the alternative that the mean is below 50, which means that we must use the more expensive oranges. That's exactly what we didn't want, but the evidence is there that the mean is too low. So we have to do something about it. All right, then the rest of these, you'll recognize them as we go along. And so we'll go over these on Tuesday, numbers 2, 3, 4, and 5. So yeah, and 6 too. Ooh. All right, so that's why I didn't want to waste any time. There's 6, we still have 5 to go. And so we can certainly finish this on Tuesday. And so we have no time to lose because these are the more complicated ones. But
Professor.
right. Yeah, go ahead.
Since like the p-value is like 7.14 and then it had the scientific notation
Right.
on the test, do you want it like in the scientific notation form or
It doesn't matter. Either one of those is fine.
All right.
Yeah. Yeah, no, and the thing is, we have to be careful though. Sometimes when people are first learning how to do this stuff, they don't notice the E and then they write the wrong answer down. Just be aware, always look for the scientific notation. And then when, by the way, this is 10, I'll just quickly remind you that this means 7.149 times 10 to the minus 4th, and that equals this number. It's tiny. It won't go into scientific notation unless it's really, really small. That by itself is enough reason to reject the null. Okay, but you should write it down.
All right.
Okay. All right. So are there any last minute questions? And if you forget that you wanted to ask a question, it's not too late to ask about everything we've done so far, like the chapter 11 problem sets. Just, when we come back on Tuesday, what you should probably do is work on these, the rest of these, make sure you understand them and we'll go over them. And then we should be ready. So just be aware, the test itself will be very, very, very similar to this, what you're seeing here. If you can do these, you can do the test. You'll be fine. Okay. Just be careful to write out the steps, read the questions carefully. And as far as I can tell, and I know this from practice, you'll have plenty of time to finish. The test itself won't be as long as what you're seeing here. You would never be able to finish this in time. So you won't have an issue with time. I know sometimes you run into that with math classes or stats classes. The test is designed to be finishable in the normal time. Okay, so I have to be very selective about which ones I pick. So, but don't worry, it'll be good. And if you know the material, you'll do well. That's the bottom line. Okay, there's no intention to trick anyone. That's for sure. All right, so what I'm going to do is post the chapter 11 problem results, and this one I'll post what we have so far. And then when we're done on Tuesday, I'll post the rest. And you can watch the video again if you want, and then you should be 100% ready by Friday. All right, so I guess I'll see you all probably in person on Tuesday. You're welcome. All right, see you Tuesday.
Oh, Professor,
Yes, go ahead.
I have two questions. So the
Okay.
p-value, it was like the 7.14. Why would we reject it there since that number is bigger than the test statistic?
No, it isn't, because the test, I mean, with the p-value, you're comparing it to alpha, not the test statistic. Okay, in other words, the
Oh, that makes a lot
p-value
of sense. Okay,
is less than alpha. The test statistic is more extreme.
okay.
These are the two things that will get the thing region, then the critical value. Either one of these mean that you reject the null.
Okay, and I have one more question.
Okay.
Oh, so the other day I was practicing the problem sets and I was like determining whether to use the Z or the T test, and I saw online, I just want to make sure this is correct. It said if what's it called? The value's under 30, you use Z. Wait, under 30, if it's over 30, use the T.
No, it's the other way around. T is for the small cases.
Okay, under 30, Z. Oh, over 30 is, wait, under 30 is T, over 30 is Z.
Right, that's right.
Okay, all right, perfect. Thank you.
Okay, anyone else?
Have a good one.
Professor, I just have a quick question.
Go ahead.
I already answered the sample midterm. I just want to know what, I'm kind of confused with number.
Oh, all right, I'll tell you what, if you need to look at these answers in advance, that's okay, but send me an email and I'll reply to it with the answers.
Okay, all right.
But in general, I'd like to hang on to them until everyone's actually worked on them. But I mean, it's clear that you have, so it's okay, but I'll just send it directly to you.
All right, thank you, Professor.
Okay. All right, anyone else? Okay. All right, good. I'll see you probably in person on Tuesday. All right, so bye.
Thank you.
Okay, bye.
Have a nice weekend.
All right, you too.